Welcome everybody once again. So we are in our 7th class for our module 2. In today's class we are going to see the kinematics of flow. So we have already studied in our previous classes, in our previous semesters, what is dynamics, what is kinetics and what is kinematics. We saw this in our first class, very first class also. So kinematics is nothing but the branch of science which deals with motion of particles without considering the forces causing the motion. Okay, so in kinematics of flow, in kinematics, the forces causing the motion are not considered. So the external force causing the motion will be equal to 0. External force is not considered in kinematics. Now, how can you describe a fluid motion in kinematics flow? So we have two different methods of describing a fluid in motion. So one is Lagrangian method and the second one is Eularian method. So generally two methods, okay, Lagrangian method and Eularian method. So in Lagrangian method, the fluid, see, when there is a fluid, you will consider a fluid particle, and when there is a flow, you will move along with the fluid particles. And at every point, that is, when this fluid particle is moving, you will determine its velocity, acceleration, density, etc. So that is Lagrangian method. So it is Lagrangian method is with respect to the fluid particle in motion. Fluid particle in motion. So you can see a single fluid particle is followed during its motion and its velocity, acceleration and density, etc. are described. See, all these velocity, acceleration are the flow properties. It is a flowing property of a fluid. Velocity is, see, if there is velocity, there is a flow. If there is acceleration, there is a flow. Okay, so these are the flow properties. Now, Eularian method, the velocity, acceleration, density, pressure, etc. are described at a point in a flow field. So you will not see in Lagrangian method, you will consider a fluid particle. Here, Eularian method, you will consider a flow field. You will consider the complete flow field. If the fluid is flowing from this point to this point, you will consider the flow field and you will take some particular point in this flow field and you will determine the velocity, acceleration, density, pressure, etc. at this point. Okay, that is called the Eularian method. Lagrangian method, you will consider a particular fluid particle and wherever it flows, what is it? What is the velocity of this fluid particle? Eularian method, in a flow field, what is the velocity and acceleration at a particular point? This is Eularian method. That is the difference between Lagrangian method and Eularian method. And the generally commonly used method is Eularian method because it is easy to understand, it is easy to analyze, it is easy to describe the motion. Okay, so Eularian method is the commonly used method for fluid flow, for studying the characteristics of fluid flow in fluid mechanics. Now we will move on to the types of fluid flow. So what are the different types of fluid flow? We have steady flow and unsteady flows, compressible and incompressible flow, or we have uniform and non-uniform flow, laminar and turbulent flow, one-dimensional, two-dimensional, three-dimensional flows. So the first type of flow is steady and unsteady flow. Steady and unsteady flows. So see, steady and unsteady flow, these flows are with respect to time. Okay, with respect to time. So steady flow, it is the flow characteristics, that is velocity, pressure, density, etc. at a point do not change with the time. So with respect to time, see, if velocity is the flow characteristics, V means velocity. If velocity is the flow characteristics, then the rate of change of velocity with respect to time, that is dou V by dou T, rate of change of velocity with respect to time in a given space, x, y, z is the space, x, y, z are the coordinates used to represent the space. So the change in velocity with respect to time will be equal to 0. That means the flow is steady. It have uniform velocity. Sorry, it has steady velocity. Steady velocity. The velocity is not changing with respect to time. That means the flow is steady. Similarly, if P is pressure, dou P by dou T at a given space x, y, z will be equal to 0. If rho is the density, dou rho with respect to T, dou rho by dou T in this given space x, y, z will be equal to 0. This is called steady flow. If it is unsteady flow, these will be not equal to 0 because there will be change. The flow characteristics changes with respect to time. So unsteady flow, the flow properties at a point changes with respect to time. So dou v by dou t in a given space x, y, z not equal to 0. Similarly, dou p by dou t not equal to 0. Dou rho by dou t with respect in the space x, y, z coordinates not equal to 0. This is unsteady flow. The next type of flow is uniform and non-uniform flow. So uniform flow, it is the velocity of the flowing fluid. The velocity of the flowing fluid. See here, we do not take all other properties. The velocity, the property of velocity. So the velocity of the flowing fluid at any given time do not change with respect to space. See, when it was a steady, for steady, the velocity with respect to time. For the steady flow, it was velocity with respect to time in the given space was equal to 0. This means it is a steady flow. Now, for uniform flow, it is just the reverse of this. That is, just the reverse of this. That means dou V by dou S at a given time will be equal to 0. See, S means it is a space x, y, z. Okay. So now non-uniform flow, the velocity of the flowing fluid changes with respect to space at a given time. So since it is changing, the differentiation with respect to t, the differentiation with respect to s space at a given time t is not equal to 0. Now the third type of flow is laminar and turbulent flow. So what is a laminar flow? Laminar flow, see, turbulent means from the name itself you can understand it will be highly zigzag flow. The flow is a zigzag, right? Zigzag manner. Laminar means smooth flow. Okay, this is called laminar flow, smooth flow. This is called turbulent flow, zigzag flow, that is turbulent flow. Laminar flow is a smooth flow. So laminar flow is also known as streamline flow. See, because you can differentiate every streams is differentiated. So it is also known as streamline flow. See, this is a streamlines. All the streamlines are differentiated. You call it as a streamline flow. It is also known as viscous flow. For example, you take a honey, right? When you make the honey to flow, what happens? It will flow in layers by layers. You can see flowing in layer by layer. You can see the movement of one layer over the adjacent layer. So that is called a laminar flow. So for the laminar flow, the fluid particles move along well-defined paths or streamlines. So well-defined paths or streamlines like this. And all the streamlines are straight and parallel. See, all the streamlines are straight and parallel. So the particles move in laminas or layers, gliding smoothly over the adjacent layers, right? So this is also known as laminar flow or streamline flow or viscous flow. Now we will see what is turbulent flow. So turbulent flow, for the turbulent flow, the fluid particles moves in a zigzag way, okay, highly in a zigzag way. So eddies formation takes place, and because of this zigzag flow, there will be a high energy loss. There will be a loss of energy, high energy loss. And this concept will help you a lot while studying the flow of fluid in a pipe. Okay, so when a fluid is flowing in a pipe, based upon the corrugations, based upon the shape, based upon the disturbances, the loss takes place. Okay, so depending upon whether your flow is turbulent or laminar. If it is turbulent, then there will be high energy loss. So this will help you while studying the flow in pipes, open channel flow, etc. Now, for flow in pipes, so you all know the advantages of pipes, right? The pipelines carrying water from one place to another. So for flow in pipes, a non-dimensional number called Reynolds number is used to determine whether the flow is laminar or turbulent. So now for this is an example, this is a practical application. Flow in pipe is a practical application. So for this case, you need to find, when you need to find whether your flow is turbulent or laminar, you can use a non-dimensional number called Reynolds number, and the formula is Reynolds number is equal to Vd by nu, where Re is Reynolds number, V is the mean velocity of a flow in pipe. This is the velocity of flow of fluid in pipe, mean velocity. D is the diameter of the pipe. Nu is the kinematic viscosity, which is equal to dynamic viscosity by rho. We have studied these characteristics in our first module. Kinematic viscosity is equal to dynamic viscosity by density. Dynamic viscosity is represented by mu and density by rho. So Reynolds number is Vd by nu, or this can also be written as Rd is equal to rho Vd by mu. Okay, so remember these both. This will help you while solving the problems. In the coming modules, module 3, 4, 5, this formula is very important. And see, once you know the density, viscosity, velocity and the diameter of the pipe, you can say whether, by after finding the Reynolds number, you can say whether your flow is laminar or turbulent. Okay, now if the Reynolds number, that is Vd by nu, if it is less than 2000, we call the flow as laminar. If it is greater than 4000, we call the flow as turbulent. And if the Reynolds number lies between 2000 and 4000, the flow may be either laminar or turbulent. It may be laminar or turbulent. Or it lies in an intermediate stage between laminar and turbulent. Now we will move on to our next type of fluid flow, that is compressible and incompressible flow. Compressible and incompressible flow. So compressible, you know, see when you have a body, when you have a box or a container like this, you have a liquid. When you are placing another container, what happens? This water will be squeezed out, right? What is the reason? This liquid is incompressible. Okay, now in general, our liquids are incompressible and gases are compressible. You can see gases can flow freely in air, right? So that are compressible. And depending upon the temperature and pressure, these things varies. The compressibility varies. Now, so what is compressible flow? The density of a fluid changes from point to point. That is, density is not constant. Okay, rho means density, not constant. See, if you take a particular portion in air and you have some kinds of air, right? So every point, you select any point, the density will be different. And when you go up in the atmosphere, every point, this is different, right? The density is different. That means it is compressible. So example is gases. Now, incompressible flow, density is constant for a fluid flow. You take any real fluid which we can see with our naked eye are all incompressible. So here density is equal to constant. So in general, for fluids, the gases are compressible and liquids are incompressible. The next type of a fluid flow is rotational and irrotational flow. Rotation, you know, rotation, right? Will rotate. So, what is rotational flow? The fluid particles while flowing along the streamlines. Streamlines means we know it flows, the fluid particle flow in layers, right? That is streamlines. So, when the fluid particle is flowing along the streamlines, they also rotate about their own axis. See, for this streamline, this is the axis. So, this particle will rotate in its axis while moving itself, while flowing, this will rotate. The next fluid particle, when it moves along its axis, it rotates about its own axis. If that is the case, you call it as rotational flow. Now, irrotational flow, the fluid particles while flowing along the streamlines, they do not rotate about their own axis. Without rotating itself, they will flow. There will not be any rotation. Now, the last type of fluid flow is one-dimensional, two-dimensional and three-dimensional flows. So, what is one-dimensional flow? Flow properties or flow parameters such as velocity is a function of time. It is always a function of time, okay? Function of time. And one space coordinate only. See, initially we saw dou v by dou t in space, that is x, y, z, right? We have defined our steady flow like this, dou v by dou t in space x, y, z. So, this is generally taken as space S. So, S, if it is three-dimensional, it will be x, y, z. Now, if the flow properties or the flow parameters, it is a function of time, right? It's a function of time. So, we will write it as f of x. So, function of time and one space coordinate only. So, it will be a function of x. So, in other two coordinates, this will be equal to 0. So, that means dou v by dou t at x is not equal to 0. But dou v by dou t at y will be equal to 0. Dou v by dou t at z will be equal to 0. That means it is a function of x alone. Otherwise, dou v by dou t at y is not equal to 0. Dou v by dou t at x is equal to 0 and at z will be equal to 0. Okay. So, the variation of velocities in other two mutually perpendicular directions is assumed negligible. Negligible, or you can assume it as 0. So, see, in all the three coordinates, velocity at x, velocity component in x direction is taken as u, velocity component in y direction is taken as v, and velocity component in z direction is taken as w. That means your u will be equal to f of x. That means it is a function of one space coordinate, f of x. V will be equal to 0 and w will be equal to 0. Similarly, for the two-dimensional flow, the velocity is a function of time and two space rectangular coordinates. And the variation of the velocity in the third dimension is negligible. That means you will have u and v, w is equal to 0. U will be a function of x and y, v will be a function of x and y, and w is equal to 0. Because the third dimension, the third direction, the variation in the third dimension is assumed to be 0. Similarly, for a three-dimensional flow, velocity, it is a function of time and three mutually perpendicular directions. That is, u will be a function of, u is f1 of, that is a function of x, y and z. V, velocity in y direction is f2 of x, y, z. Velocity in the z direction is w is equal to f3 of x, y, z. These are functions f1, f2, f3. Just to differentiate, we have given the numbers 1, 2, 3. It's a function of x, y and z. If the velocity components, see in symbol, if the velocity components are a function of all the three mutually perpendicular direction, then it is 3-dimensional. If any one is 0, then it is 2-dimensional flow. And if any two directions it is 0, then that becomes 1-dimensional flow. So what we have seen today is what is kinematics, then how the fluid flow is described, that is Lagrangian flow and Eularian flow. The generally accepted one is Eularian flow, and what are the different types of fluid flow: steady and unsteady flow, uniform and non-uniform flow, rotational and irrotational flow, compressible and incompressible flow, laminar and turbulent flow, and one-dimensional, two-dimensional and three-dimensional flow. So thank you for today. Thank you for listening.